Hello there, welcome to your 7th webinar. In this webinar, we will going to have a step-by-step walkthrough to building your own recurrent neural network. And in here, we only will use NumPy and we will not use any other libraries. So you'll actually get familiar with the underlying steps. So as you already learned in your courses, a recurrent neural network is a simple neural network that has a memory element to it, which it makes it great for NLP tasks. And for creating your own recurrent neural network, you only need to do 4 steps. And at the very start, you need to create your own RNN cell, which is just this one. As you can see in here, we zoomed out. At the start, you will only build this RNN cell for forward pass, and on the second step, you will build your RNN forward pass, which is only repetition of these RNN cells. At the third step, you will create your own RNN cell, but this time backward. And at the fourth and the last step, you build your own backward pass of RNN, which is a repetition of RNN cell backward. So that being said, let's start by importing NumPy, since that is the only library we are going to use. So before actually starting it, let's write down the softmax function. And if you have a hard time to remembering it, you can simply just Google it and you will get the formula right away. So let's write that down. At the very start, we want to get the exponential of x minus the maximum number in Rx. And for our softmax function, which is simply this, and it's divided to sums of it, root axis of 0. Okay, now we have our softmax function, and that was all. So let's start by creating the RNN cell forward. And if you look at the function that we want to create, as an input we will get our input data, which is this, and also we will get a hidden state of previous, which is this. And also we will get a parameter dictionary, which if you read through this, you will notice that we will get 3 weight matrices and also 2 biases. And you can see that actually this is the weight matrix of X, weight matrix of hidden state, weight matrix of Y, and also plus biases. And we will get all of this as input, which at the very start we will just randomly choosing it. And for our forward cell RNN, we will use this formula. So at the very start, what we want to do is to actually retrieve the parameters. And these parameters that I have already told you, it will be given to you with this parameter dictionary. So for getting your weight matrix for the input data, you will just write down parameter dictionary and you will write down wx. And same as the other weight matrices, you will just write down parameter dictionary and also write down ws for hidden state and also wy for our output. Also same thing applies to our biases, which this is biases for the hidden state and also bias for the output. And after getting this parameter, these weight matrices and biases, what we want to do is to compute the next activation state, which this is the, if you look at it, this is the activation function of the input data multiplied by its weight matrix plus hidden state multiplied by its weight matrix. And that is it. We will want to write this as a code. So let's write it down. We will say np tangent, which we will use it as an activation function, and also we will say np dot which is wx and xt. So far we did this. Now let's also multiply this hidden state by its weight matrices, which is, let's say, np dot ws and stprev. Okay, now and also at the very end we will add the biases for hidden state. So the next step after getting our activation step, we want to compute the output. And in here it depends whether we want to do classification or regression. In here it shows as a regression problem, and since we want to consider classification, so we also would extra activation function in here as well. So let's compute this. We'll use a softmax function that we have already created it, and in here we will multiply the wy by stnext, which is next hidden state multiplied by its corresponding weight matrices. And also we have to add the bias, which is the bias of hidden state. And now we have computed our output of our cell. Let's also store all of the variables, which, if you read through it, is a hidden state at t, hidden state at t-1, hidden input data at t, and also parameter dictionary. And we want to store it in just one tuple. So say stnext, stprev, xt, which is input, and also parameter dictionary. And that is it. We are done with the first step of creating your own recurrent neural network. Now let's test it. Before testing it, we have to compute this forward step for RNN cell. And at the start we will get a random number for our input data, then we will get some random number for our hidden state at time t-1. We will get our weight matrices for input, hidden state, and output, and also we will get two biases. And we stored all of it into one dictionary. So let's compute this based on this data that has been given. We want to compute this, so we will say RNN cell forward, which is this function, and as our input we want to get this, and as our previous hidden state we want to get this. Oops. And as our parameter dictionary we will get these parameters. So now we have already gotten our next hidden state, output, and also all of our parameters. And you can actually go check out the numbers, but now we have finished with computing the RNN cell for forward pass. The next step is to create the total forward pass, which is repetition of these cells. So now the function that we are writing here, it will take input data, it will get our initial hidden state, and also parameter dictionary, which is weight matrices plus biases. And in here we want to output the hidden step at each time step, and also prediction, and also the tuple of all of our parameters that we need. At the very start we have to again retrieve the dimensions, which I have already actually write this down for you. Each of them should be what type of dimension should it have. So for getting the dimension of x and t of x, we will get it from input data, which is x. We will just get a shape and we will have these dimensions. Next we want to get the dimension of ny and also ns, And the way we get it, we will just say parameter dictionary, and also we will choose wy, which is a weight matrix of output, and we will get a shape of it. Now we have all of the dimension that we need. All of them has been laid out for you, so you can just read it out, each of them, what type of weight shape should it have. Then we want to initialize the state and also predicted y with zeros, which later we will update these variables. Let's start by hidden state. We will say np.zeros, and for the shape, if you look at this, S has this shape, so we can just copy paste it. And for the prediction, the shape it should have is this, so we will initialize it with zeros. Shape nym_t of x. The next step, we will initialize our next hidden step, which at the very start we will start by the first hidden state, and then we will change it. So now, since I told you that the RNN forward is only the repetition of this RNN cells that we have already created, so we want to loop over all of our time steps. And at very start, we want to update the next state and also predicting the output and also getting the cache. So we can say is next yt cache RNN cell forward, which we created in the first step, and as our input we will get x, but every time it should be different, so each time it will go different different inputs. And so as our previous hidden state, we will choose this is next, and also for our parameter dictionary, we use a parameter dictionary that it will be given by the input. The next step is to save the next state into our hidden state, which we want to save this into our S. So we will say S. As each time step it will be different, and we will update it with S of next. And also we want to do same thing for our prediction. We want to update our prediction, which we will go through this prediction voice that we initialized with 0, and we will update it with this y of t. And like similar as the before, we will say ypred, which as at each iteration will be different, and we will update it with y of t. And also we will want to append all of this cache into this empty list. Append cache. And that is it with our RNN forward. So now we have created our function. Now let's compute it, which at the start we will create our input data, our initialized hidden state, weight matrices for input, hidden state, and output, and also our two biases, and we've put all of these parameters into a dictionary. So now let's compute this forward pass, which RNN forward. As of input, we will get this, and as our initialize in the first hidden state, we will use this, and also for our parameter dictionary we use this. Okay, now we have computed our forward pass. Now we are 50% done with creating the recurrent neural network, which was forward pass. The third step and the fourth step is to creating the backward propagation. So let's start by writing down the function for RNN cell backward. So what we want to do at the very start to retrieve all of the values from the cache, which if you look at it, you will notice that it will return the next hidden state, previous hidden state, and input data at time t, and also parameters dictionary. And we'll make it equal to cache, which we will get it as an input. And also let's retrieve all of the weight matrices and also biases. We'll say parameter dict, and we will say just wx. You can repeat the same thing for the rest of the parameters. Let's say this ws, which is a weight matrix of hidden state. This is wx, weight matrix of input data, and also biases for hidden state, biases for output. So now let's compute the gradient of the tanh with respect to next hidden state, which you do not really need to know by heart. It's just a formula, and the formula is as follows. We say 1 minus next hidden state, next hidden state in power of 2, then we will multiply it by gradient of next hidden state. So now let's compute the gradient of loss with respect to wx. So at the very start we will compute the gradient of gradient of xt, which is the input data. We will say it's a dot product of its weight matrix transposed by tanh, gradient of tanh. And also for gradient of wx, which is the weight matrix of input, we will say np dot d tanh with gradient of xt. And we also use transpose of it. So now also let's compute the gradient with respect to weight matrix of hidden state, which for computing the gradient of previous hidden state, we will say it's a dot product of the hidden state weights transposed with d tanh. Also for gradient of weight matrix of hidden state, dws, we will say it's a dot product of d tanh with the previous hidden state transposed. And at the very end, let's also compute the gradient with respect to biases, which we will say it's sum of tanh. We will sum the axis of 1. Also we want to keep themes. Okay, so now we finish with the RNN cell backward. Let's also write down the testings. So now here we will have an input data, previous hidden state, weight matrices, biases, and also all of these parameters into a dictionary. So at the very start, let's compute the single forward step for our RNN cell, which we have already created. The name of the function is RNN cell forward. Then as an input we will get this. As our previous hidden state we will get this. And also as our parameter dictionary we will get this. Now in here also we create a random number for r, or the gradient of the loss function with respect to the next hidden state. And also let's also compute the backward pass of the RNN cell, which we will say RNN cell backward. So in here we'll get this, and also we will get the cache, which is here. So now we have computed the backward cell. The last step is to create the backward pass, which is a repetition of this backward cell. And that is it. After creating this backward pass, we have created our fully recurrent neural network. So let's start by retrieving the first cache at the time t equal to 1. So we have to first write down caches and also input data from which we will get it from our input. And also for getting our first caches, it will return 4 variables. The first one is the first hidden state, then S0, then input data, then also parameters. Well, let's put this on a tuple. So now also again let's retrieve the dimensions, which if you read through this you can get it very easily. For getting the dimension of n of s and t of x, we will just say it's a gradient of hidden state shape. And also for getting a n of xm, which is the shape of input data, we'll say x1 that shape. And also let's initialize all of this gradient, which is the gradient with respect to input data. We will initialize all of this with the 0 matrices using NumPy. So let's say shape of t of x is this. Also gradient with respect to weight matrix of input data, we'll say it's also 0 with the shape of dwx. The shape is this. The gradient with respect to weight matrix of hidden state, the shape is equal to this. Also gradient of the biases in our hidden state is zeros. The shape is equal to, let's see, n of s1. So that is exactly what we will write. And also np dot zeros shape. So the shape is nsm. And also lastly, the gradient with respect to the previous hidden state is equal to shape of, let's see, ds prev, which is this. So now we have initialized all of our gradients. And as I said, since this RNN backward is a repetition of this RNN backward cell, so we will have an iteration with a range of our time steps. At the very start inside our loop, we want to compute the gradient at each time step. And also we will use this function that we have right, RNN cell backward. So we want to do it at each iteration. And the gradient with respect to next hidden state is equal to, let's see, okay, we have this as our input, which we will get it at each iteration. So we will say t. Okay, and also the next one is cache, which again we have here. Cache, since there is multiple cache inside, we want to again have the t value. So now also retrieve all of the derivatives from our gradients, and let's say gradients, which is this, we'll say just d of xt, and we can just copy paste this for the retrieving the rest of the gradients. The second one we will say d of s prev, then we will say d w x, oops, next we will say dws, next we will say dbs, which is a gradient of bias in our hidden state. So the last thing that we want to do inside our loop is to increment our global derivative with respect to parameters, which we will add their derivative at each time steps. So we can say derivative of x, we want to get the relevant value in that iteration, and we want to make it equal to d of x of t. And also for dwx, we want to increment it by dwt. For our dws, we want to increment it with dwst. For our dbs, which is for biases, we will increment it with this. So now also let's update the initialize in the first hidden state. We will make it equal to ds.prev, which is this. And also we put all of our gradient in a dictionary, and then we will return it. So that is it. We write down the function for RNN backward. Now let's do the required testing. So in here we have our input data, we have our first hidden state, we have our weight matrices, we have our two biases, and also we have a dictionary that contains all of the parameters. So now let's compute the forward pass for our RNN. Again, we write down the function which is called RNN forward. As an input, we will get this. As of initial hidden state, we'll get that. Then parameter dictionary is this. So now let's also compute the backward pass, which is RNN backward, and the value of d of s, which we have already created a random number of it. Then also caches, which is again, where is it? It's here. Okay, let's see what was the problem. Okay, apparently I have to put d. Okay, now we have created our recurrent neural network, and you can do the same steps if you want to create, I don't know, like LSTM, GRU, and it is just a very few changes, and it is not a very big change, so it's very easily can be modified for converting to those architecture. And if you're interested for extra resources, check this out. Now after this, we want to create an encrypted language using RNN. But in here, we won't use the RNNs that we have created here. In here, we will use the actual libraries. More specifically, we will use Keras, which you will see how easy and fast you can reach to your result. So let's start by importing the libraries, which for the loading the dataset we will use a library. This file I have already provided for you, which is in the same directory as your files. This library we use it only for loading the dataset. So there is two type of dataset. One is called codes and one is called plain text. The plain text is the actual text. It's just some English words, and also codes are encrypted version of that plain text. So let's import them, and now we will see it exactly how they're related. So we'll say load data. For me, the files are in dataset directory, and the name of the call are cipher. Let's call this helper again. Load data. Again in the same directory. This time it's called plain text. Plain text. Okay. Let's import this. Also, let's take a look at the first sentences in each of the actual English sentence and also the encrypted version of it. Let's say print sentence plain text, the first item. Also print out the encrypted version, which is code. Okay, now we have our both sentences and our encrypted version. As you can see, this is converted to this to this, and it's not like there is always converted to this. Like if you look at this time is converted to YMJ. This time is totally different. So let's pre-process it. So we will import the NumPy library. We'll say pre-processing text. We'll import the tokenizer. Again from keras pre-processing, but this time we will get from sequence. We'll import for path sequence. So now let's write down the function for pre-processing our text. We will call it pre-process text. We will get a list of strings. So at the very start, we will initialize the tokenizer. And also remember that in here we want to tokenize not based on words, but based on each characters. For example, this is one character, this is one character, and we want to tokenize all of it based on character. So tokens, tokenizer, we will say already converted to lowercase, true, which is, this is already default, so I just put it for further reminding. We will say splitted with empty strings. Also we want to be character level, as I said, true. And also it has a filtering, which this is for the, we won't use it. This is for like if you want to delete all of this question mark, you can change it accordingly. So now let's also fit the tokenizer to our text. We will say character tokens fit on text, and we will apply this to list of strings. And now let's return these character tokens, but we want to say convert the text to sequence. Sequences. Okay. List of string. character tokens. So now let's also apply this preprocessing function to our both encrypted version and also the actual English version. We will call the codes version codes preprocessed, and also codes tokenizer is equal to preprocessed text, which we will apply this on codes. For the plain text, we will say plain text preprocessed plain text tokenizer. Tokenizer, which we will apply this preprocessing to our plain text. So, okay, I forgot to put texts to sequences. Okay, now we have already preprocessed all of our data sets. So we can just take a look at the first sentence again, see like how much it changed. We will say sentence, go to next line, plain text, first item. Again, go to next line. So now we want to print out the preprocessed version, preprocessed sentence, go to next line, plain text, preprocessed. Also we get the first item. So you can see that we converted, we tokenized it. Now it is all numbers, which is totally ready to go to our neural network. But before that, we have to also apply zero padding, because each sentence are longer, some of them are shorter, and we want to be all of them same size. Which, if it was shorter, we will add 0. If it was longer, we will just cut it out. Let's actually write down the function padding, which we will get a list of strings again. And also we will get a length, like if it was bigger, cut, if it was less, then add zeros. So let's add, we will just define that none for now. So define length if it is not defined. So if it wasn't, we didn't specify the actual length, we can automatically, it will detect like how much should be the length, which it is the maximum. So now we want to iterate through, let's say for I text in our list of strings and get length of each of it. This is going to be, we will get this, we will iterate through each of the sentences, we will get the length, then we put it into our list. Then among this list we will get the maximum of it, and we will define that as our length. So let's say add padding, pad sequence, which is a recurrent library. You apply this to a list of strings with the max length of length, and also padding of posts. Okay, now let's return it. Now let's apply this to this preprocessed text that we have. Again, we have to apply this 2 times, one for the codes and one for the plain text. Let's start with the codes. Again, we will call it preprocess. Padding codes preprocessed. Plain text preprocessed. Padding plain text preprocessed. So now we added our padding The very last thing that we want to do in our pre-processing section is to, as you read this, like read through the Keras documentation, for since we are using a sparse categorical cross entropy, we need to convert our label into a three-dimensional. So we can say plain text preprocessed, and we will make it equal to plain text preprocessed, which will reshape it. We will say keep the current shape, and also add one extra dimension to it. Now we have our 3D labels, so we are totally ready to create our model, and you will see how it goes. So let's start by importing all of the libraries that we are going to use for creating our model. So at the start we will say layers, let's say input, dense, and also let's say GRU, and time distributed. So also from keras.models, import model, from keras.optimizers, import Adam, and also for layers we want to import activation as well, from keras.losses. As you guessed it, from the preprocessing section we use sparse categorical cross entropy. Now very lastly we want to save our model, so we use callbacks and model checkout. So now let's write down the hyperparameters. Like one of them are learning rate, one of them are the number of units in our GRU, and our batch size, number of epochs, and we can also define, since we didn't already split this dataset into training and validation, we can also define a validation split, which the keras itself will do it. We'll say 20%. Let's also write down each of it. Later you can also change this for making your model better. We'll call it your unit, for example, 64. For our batch size we can say 32. For number of epochs, let's choose something small like 5. So before putting our input to our model, we need to reshape it because it simply won't work. So we'll say temporary x, let's add padding, list of string is equal to codes processed. Oops, there's two versions. This one. Okay, now also we want to say length, which we will say plain text excuse me, plain text preprocessed. We'll get a second part of it, sorry, 1, since it starts at 0. Again we will say temporary x, we will reshape it, so -1, in here plain text preprocessed, shape, get the last 2, and also we want to add the extra dimension. So now our input is ready for going to our model. now we reach to the most interesting part, which we will design the actual architecture of the model. In here we just put a simple model so it can run faster. At the very start we will define the input model, which is input is from Keras, is a temporary x. It will get a shape of after 1. Also the first RNN layer we will use GRU. The number of units we already defined a GRU unit. And also let's say return sequences true, and we want to get this input model and get it. Okay, now let's define the logics, which is first let's do the dense, which the unit is let's say length of the plain text tokenizer. We will get a word index of it, and also we will add 1 to it, to that length. Then we will apply the time distributed, and we want to get this RNN. Now let's finalize our model, which we will get this input model, and also we will get an activation, let's say softmax. We will put it for logics. Great. Now let's take a look at the summary of the model. Okay, as you can see, it's just a 2-layer. We have one GRU layer and one dense with the time distributed. Now let's compile the model. We will say model.compile with the loss function of sparse categorical cross entropy, with the optimizer of Adam, with the learning rate that we have already created. So for metrics we want to have the accuracy. Now it's ready for fitting. Before fitting, let's define a checkpoint for saving only the best ones automatically. Pointer model checkpoint. Let's define a path for it. We'll say saved models. Like we'll choose a name somehow like weights.best.deciphering HDF5. And also we want to do verbose of 1. And also we want to save best only true. Now let's write down the training part. Model.fit, which will get a temporary x that we already created it. For our y we will define plain text preprocessed. Let's go to the next line. We will do batch size, which again we define it. We define the epochs, which again we define it. Also validation split, which we said it want to be 20% again. Also we have to specify that we have a callbacks. We will define it into a list. And lastly, we will say verbose of 1. Okay, batch size. I forgot to put the T. Now our training is started. It is pretty fast. So let's, until it gets trained, we write down the function for prediction. So when it gets finished, we actually can start predicting. So for writing down a function for prediction, what we want to do is to write down at the start, write down a function which it will convert logits and to a text, since the prediction is going to be number and it will not give the prediction as a text. So we can actually say logits to text, and as our input we get the logits, and also we will get a tokenizer, and in here we will get, at the very start we will get index to words, which is very simple. Let's say index to words, define a dictionary. We will say word ID. We will say tokenizer that we will have it in our input, and we'll say word indexed, and we will get the items of it. And since this is an index to word, we will say ID to word. So now we have our index to words. We want to also add pad because sometimes we don't have the actual word that we want to. When we want to have index to words, there's some words that it is not available, so we put pad at the start of index to word. Now let's get the text, prediction text. Use join. So now let's iterate through prediction. We'll get the argmax of the logits with the axis of 1, which we want to have the index to word of that prediction in that iteration. Now we will just return the text. As you can see, our training has been finished. Now we have an accuracy of 95%, which is very great for just 5 epochs. So now let's start by predicting. Let's say prediction. Let's predict the first item into our temporary input. And it is important to put it like this because of the dimensionality only. Now let's convert the logits into text. So predicted text, logits to text. So we'll get the prediction, and as our tokenizer, we will get a plain text tokenizer. Excuse me. Now let's print out the result. So as you can see, we exactly predicted it. So let's do this. Let's also get the first item, and so we can exactly see. Oops. So this is the actual text, and this is the prediction that we predicted based on the encrypted words. But you can see how powerful stuff we can make with this simple model. And if you're interested, just check these two resources out. Thank you very much for putting your time. I hope you enjoyed this webinar. Thank you.